Welcome to the Shell Scripting course. By the end of this course, you'll be able to create shell scripts with ease. You'll learn how to take complex, tedious, and repetitive tasks and turn them into programs that will save you time and simplify your life on Linux, Unix, or Mac systems. In this course, we'll cover exactly how to get started writing shell scripts, what the shebang is, and why you need one in every script you write. You'll also learn how to create and use variables in your script. We'll talk about testing and decision making. Next, you'll learn how to accept command line arguments with your script and how to process those. You'll learn how to accept input and write output. You'll learn decision making structures like if statements. We'll talk about the importance of exit statuses and how to use those. Next, you'll learn how to create and use functions in your scripts. We'll be talking about the use of wildcards and how to use those in conjunction with things like for loops. You'll learn how to simplify complex if statements by using something called a case statement. We'll talk about logging and some easy ways you can implement logging inside your shell scripts. You'll even learn some debugging tips and also some really common errors that people make when writing shell scripts and how to avoid those. Also in this course, we're going to talk about some specific bash shell options that you can use to make your life easier. Those are the major highlights, but there's much more in this course. Okay, let's get started. This course comes with a download, and when you extract the contents of this compressed file, you'll see a subdirectory created called shell-scripting-course. In that subdirectory, there will be directories for each of the sections of the course. For example, the debugging section will have a directory. And then inside that directory, there will be two more directories, one lesson directory and one practice exercise directory. The lessons directory contains all the shell scripts that you'll see me using during the lessons and presentations during this course. The practice exercises contain the practice exercise assignments as well as the solutions. To get to the downloads, you're going to need to click toward the top right of your screen where there's a little download arrow. And then next, it'll show the downloadable resources, and that's where you can download the files that you can use with this course. I just wanted to take a few seconds to introduce the next two videos that you're about to watch. They contain the most important aspects of shell scripting. The content in those videos will take you really far. You'll be able to do almost anything you want with a shell script if you really understand what's covered. Later on in the course, we'll be diving deeper into some of those topics presented in those videos, and you'll learn advanced techniques around those topics that will help take care of edge case scenarios. I'll also introduce you to some other techniques that aren't covered in the next two videos that can take your shell scripting to the next level. I recommend that you watch these next two videos at least twice and take the time to practice the techniques you learn in them. Okay, let's get started. In this lesson, you'll learn exactly what scripts are, the components that make up a script, how to use variables in your scripts, how to perform tests and make decisions, how to accept command line arguments, and how to accept input from a user. A script is a command line program that contains a series of commands. The commands contained in this script are executed by an interpreter. In the case of shell scripts, the shell acts as the interpreter and executes the commands listed in the script one after the other. Anything you can execute at the command line, you can put into a shell script. Shell scripts are great at automating tasks. If you find yourself running a series of commands to accomplish a given task and you need to perform that task again in the future, you can and probably should create a shell script for that task. Let's look at a simple shell script. Before you can execute the shell script, make sure that it has the executable bit set, so we can chmod at 755 for instance. If the script is in your path, you can simply type in the script name and it'll execute. If it's not in your path, then you'll need to give it a relative or full path to your script. In this case, we'll pretend that I'm sitting in my home directory, and this is a script that I just created, and I want to execute it out of my home directory. My home directory is not in my path, so I'll do // and the script name to execute it. You'll notice that the first line of the script starts with a £, then an exclamation mark, and then that is followed by the path to the bash shell program. The number sign is very similar to the sharp sign used in music notation. Also, some people refer to the exclamation mark as a bang. So $exclamation mark can be spoken as sharp bang. The term shebang is an inexact contraction of sharp bang. When a script's first line starts with a shebang, what follows the shebang is used as the interpreter for the commands listed in the script. Here are 3 examples of shell scripts, each using a different shell program as the interpreter. When you execute a script that contains a shebang, what actually happens is that the interpreter is executed and the path used to call the script is passed as an argument to the interpreter. You can prove this by examining the process table. Let's start this script called sleepy.sh in the background and look at the process table. You can see that what is actually running is /bin/bash space /sleepy.sh. Let's use a full path to the script. In this case, /bin/bash has been executed with the path to sleepy.sh, which is /temp sleepy.sh. Also, you can see that bash is executing the sleep command, which is the first and actually only command in this shell script. If you do not supply a shebang and specify an interpreter on the first line of the script, the commands in the script will be executed using your current shell. Even though this can work just fine under many circumstances, it's best to be explicit and specify the exact interpreter to be used with the script. For example, there are features and syntax that work just fine with a bash shell that won't work with a C shell. Also, you don't have to use a shell as the interpreter for your scripts. Here's an example of a Python script named hi.py. If you're interested in Python programming and scripting, you can see my book, Python Programming for Beginners. You can find more information about it at linuxtrainingacademy.com/python-book. Let's get back to shell scripting. You can use variables in your shell scripts. Variables are simply storage locations that have a name. You can think of variables as name-value pairs. To assign a value to a variable, use the syntax variable name equals value. Make sure not to use any spaces before or after the equal sign. Also, variables are case sensitive, and by convention, variable names are in all uppercase. To use a variable, simply precede the variable name with a $sign. You can also enclose the variable name in curly braces and precede the opening brace with a $sign. The curly brace syntax is optional unless you need to immediately precede or follow the variable with additional data. Here's an example. Let's say you want to add the letters ing to the value that's stored in the my shell variable. To do this, you would use $, curly brace, the variable name, closing curly brace, and then ing. If you do not encapsulate the variable name in curly braces, the shell will treat the additional text as part of the variable name. Since a variable with that name does not exist, nothing is put in its place, as in this example. You can also assign the output of a command to a variable. To do this, enclose the command in parentheses and precede it with a $sign. In this example, the output of the command hostname is stored in the variable server name. In this sample output, the server name is Linux SVR. You can also enclose the command in backticks. This is an older syntax that is being replaced by the $sign parentheses syntax. However, you may see this in older scripts. Variable names can contain letters, digits, and underscores. They can start with letters or underscores, but cannot start with a digit. Here are some examples of valid variable names, followed by some examples of invalid variable names. The valid variable names have a mixture of uppercase and lowercase letters and the underscore and digits. All that is fine. In the invalid case, you see a variable that starts with a digit, which is an invalid syntax for a variable name. The other 2 examples contain dashes and @ signs, which are not valid characters to be used in variable names. Scripts are designed to replace the need for a person to physically sit at a keyboard and type a series of commands. What if you have a task you want to automate, but it requires different actions based on different circumstances? If you're typing in the commands, you can take the time to look at a status and then make a decision based on that status. In shell scripts, you can do the same thing. You can do this with tests. To create a test, place a conditional expression between brackets. The syntax is open bracket, condition to test for, and close bracket. You can test for several types of situations. For example, you can compare if strings are equal, if a number is greater than another, or if a file exists. This test checks to see if Etsy password exists. If it does, it returns true. Said another way, the command exits with a status of 0. If the file doesn't exist, it returns false. That is, the command exits with a status of 1. If you're using the bash shell, you can run the command help test to see the various types of tests you can perform. You can also read the man page for tests by typing in man test. Here are some of the more common tests you can perform. -D tests to see whether what follows is a directory. If it is a directory, it returns true. -E returns true if the file exists. -F returns true if the file exists and it is a regular file. For example, it's not a symlink. R returns true if the file is readable by you. S returns true if the file exists and it's not empty. -W tests to see if the file is writable. -X tests to see if the file is executable. If it is, it returns true. -Z followed by a string will return true if the string is empty. However, -N will return true if the string is not empty. If you place two strings on either side of an equal sign, then it will return true if those strings are equal. You can also test if two strings are not equal by using an exclamation mark before the equal sign. You can also do number comparisons like -EQ to test if the numbers are equal, or NE for not equal, LT if the first number is less than the second number, LE if the first number is less than or equal to the second number, GT if the first number is greater than the second number, and GE will return true if the first number is greater than or equal to the second number. So now that you know how to determine if a certain condition is true or not, you can combine that with the if statement to make decisions in your scripts. The if statement starts with the word if and is followed by a test. The following line contains the word then. Next is a command or series of commands that will be executed if the tested condition returns true. Finally, the if statement ends with fi, which is simply if spelled backwards. Here's an example script. Note that it's a best practice to enclose variables and quotes to prevent some unexpected side effects when performing conditional tests. You can also perform an action if the condition is not true by using an if-else statement. Simply insert the else keyword and follow that by the commands you want to execute if the condition is not true. So let's update the script to perform an action if the statement is not true. Because my shell equals bash evaluates to false, the statements following else were executed. You can also test for multiple conditions using elif. The word elif is a contraction for else if. Like if, follow elif with a condition to test for. On the following line, use the word then. Finally, provide a series of commands to execute if the condition for the elif evaluates to true. Here is an updated version of the script using elif. If you want to perform an action on a list of items, use a for loop. The first line of a for loop starts with the word for, followed by a variable name, and then a list of items. The next line contains the word do. Place the statements you want to execute on the following lines, and finally end the for loop with the word done on a single line. Essentially what happens is that the first item in the list is assigned to the variable and the code block is executed. The next item in the list is then assigned to the variable and the commands are executed. This happens for each item in the list. Here's an example script that shows how a for loop works. You'll see that there are 3 items in the list: red, green, blue. The for loop executes 3 times. The first time, red is assigned to the variable color, and the echo color command is run. And the second time, green is assigned to color, and the third and final time, blue is assigned to the variable color, and the command is executed. It's also a common practice for the list of items to be stored in a variable, as in this example. This script renames all of the files that end in JPG by inserting today's date before the original file name. Here's what happens when you run this script. You'll see that the bear.jpg file becomes today's date-bear.jpg, and this continues for every file that ends in JPG. Positional parameters are variables that contain the contents of the command line. The variables are $0 through $9. The script itself is stored in $0. The first parameter is stored in $1, the second in $2, and so on. Let's take this command line as an example. The contents of $0 are script.sh, $1 contains parameter 1, $2 contains parameter 2, and $3 contains parameter 3. This script, called archiveuser.sh, accepts a parameter which happens to be a username. Anything that follows the pound sign is a comment. The only exception to this is the shebang on the first line. Everywhere else in the script where a pound sign is encountered, it marks the beginning of a comment. Comments are dutifully ignored by the interpreter as they are for the benefit of us humans. Anything that follows the pound sign is ignored. If a pound sign starts at the beginning of a line, the entire line is ignored. If a pound sign is encountered in the middle of a line, only the information to the right of the pound sign is ignored. Here's what the output looks like when we execute the script. Instead of referring to $1 throughout the script, let's assign its value to a more meaningful variable name. In this case, let's assign it to the variable called user. The output remains exactly the same. You can access all the positional parameters starting at $1 to the very last one on the command line by using the special variable $@. Here's how to update the script to accept one or more parameters. Now you can pass in multiple users to the script, and the for loop will execute for each user that you supplied on the command line. Here's what the script would look like if we passed in 2 users, in this case, Chet and Joe. If you want to accept standard input, use the read command. Remember that standard input typically comes from a person typing at the keyboard, but it can also come from other sources like the output of a command in a command pipeline. The format for the read command is read-p, a prompt to display, and a variable name. This version of the archive user script asks for the user account. In this example, I ran the script and typed in the username Mitch. Let's review. The first line in a shell script should start with a shebang and the path to the interpreter that should be used to execute the commands listed in the script. To assign a value to a variable, start with the variable name followed by an equal sign, then followed by the value. Do not use a space before or after the equal sign. You can access the value stored in a variable by using $variable name or $curly brace variable name close curly brace. The latter form is required if you want to proceed or follow the variable with additional data. To assign the output of a command to a variable, enclose the command in parentheses and precede it with a $sign. Perform tests by placing expressions in brackets. Tests are typically combined with if statements. Use if-else, or if-elif-else statements to make decisions in your scripts. To perform an action or series of actions on multiple items, use a for loop. To access items on the command line, use positional parameters. The name of the program is represented by $0. The first parameter is represented by $1, and so on. To access all the items on the command line starting at the first parameter, or $1, use the special variable $@. You can place comments in your scripts by using the pound sign. If you would like to accept user input, in this lesson, you will learn how to determine the exit status of a given command. You'll learn how to make decisions in your scripts based on the exit statuses of various commands. Finally, you'll learn how to use exit statuses in your own scripts. Every time a command is executed, it returns an exit status. The exit status, which is sometimes called a return code or exit code, is an integer ranging from 0 to 255. By convention, commands that execute successfully return a 0 exit status. If some sort of error is encountered, then a non-zero exit status is returned. These return codes can be used in your script for error checking. It can be a simple check like checking for a zero return code, or it could be more complex like checking for a specific error code. If you want to find what the various exit statuses mean, you have to consult the documentation for the given command or look at its source code. You can use the man command or info commands to read the documentation for most commands on your system. For example, in the grepman page, I can see that it will exit with a status of 0 if the search pattern is found and 1 if the search pattern is not found. The special variable $? contains the return code of the previously executed command. In this shell script, the ls command is called with a path to a file that doesn't exist. Immediately after the ls command is executed, the return code of that command is displayed on the screen using echo $? This will display a 2 to the screen. Remember that non-zero exit codes indicate some sort of error. Had the file /not/here existed and ls was able to display information about that file successfully, the exit status would have been 0. You can use an exit status of a command to make a decision or perform a different action based on the exit status. In this example shell script snippet, we use the ping command to test our network connectivity to google.com. The -c option for the ping command simply tells ping to send just one packet. After the ping command is executed, we check the exit status. If the exit status is equal to 0, then we echo to the screen that google.com is reachable. If the exit status is not equal to 0, we echo to the screen that google.com is unreachable. This example just checks for an error condition. In the if statement, we look for a non-zero exit status. If $? does not equal 0, then we echo that the host is unreachable. If the ping command succeeds and returns a 0 exit status, then the echo statement is not executed. We can assign the return code of a command to a variable and then use that variable later in the script. In this example, the value of $? is assigned to the return_code variable. So return_code contains the exit status of the ping command. In addition to using if statements with exit statuses, you can use logical ands and ors. The double ampersand represents and, while the double pipe represents or. You can chain together multiple commands with either ands or ors. The command following a double ampersand will only execute if the previous command succeeds. Said another way, the command following a double ampersand will only run if the previous command exits with a 0 exit status. In the example on the screen, makedir/temp/bak is executed. If it succeeds and returns a 0 exit status, then, and only then, will the cp command be executed. In this example, you can see that there is no need for the cp command to be executed if the directory wasn't able to be created. The command following a double pipe will only execute if the previous command fails. If the first command returns a non-zero exit status, then the next command is executed. In the OR example, the first cp command, cp_test.text/temp/bak, is executed. If it succeeds, the next cp command is not executed. In this example, if the first cp command succeeds, then we have successfully created a backup copy of test.txt, so there's no need for another backup copy of that file. If the first command fails, however, then the second command is executed. In this example, if test.txt can't be copied into /tmp/bak, then an attempt will be made to copy it to /tmp. With an OR, only one of the two commands will successfully execute. Let's revisit our earlier example. Instead of using an if statement, here we are using an AND. In this example, if the ping command exits with a 0 exit status, then google.com reachable will be echoed to the screen. Here we are using an OR instead of an if statement. In this example, if the ping command fails, then google.com unreachable will be echoed to the screen. If the ping command succeeds, then the echo statement will not be executed. If you want to chain multiple commands together on a single line, you can do that by separating those commands with a semicolon. The semicolon does not check the exit status of the previous command. The command following a semicolon will always get executed, no matter if the previous command failed or succeeded. In essence, separating commands with a semicolon is the same as putting those commands on separate lines. I rarely use semicolons to separate commands in shell scripts, but you might see this in existing shell scripts. Of course, you can always use this syntax on the command line outside of a shell script. Not only do normal commands return an exit status, but shell scripts do as well. You can control the exit status of your shell script by using the exit command. Simply use the exit command in your script and follow it with a number from 0 to 255. If you do not specify a return code with the exit command, then the exit status of the previously executed command is used as the exit status. This is also true if you do not include the exit command at all in your shell script. Again, in that case, the last command that was executed in your shell script will determine the return code of your entire shell script. You can use the exit command anywhere in your shell script. Whenever the exit command is reached, your shell script will stop running. In this example, we are controlling the exit status of our script with the exit command. If the ping command succeeds, a return code of 0 is received. This means that the test in the if statement is false and the code block will not execute. This means that the exit 0 line is executed. This stops the execution of our script and returns a 0 as the exit status. If the ping command fails, then a non-zero exit status is received. This makes the if statement true and the echo command and exit 1 commands are executed. The exit 1 command will stop the execution of the script and return an exit status of 1. Now your shell script can be called by another script and its exit status can be examined just like any other command. Since you control the exit statuses, you can make them have a significant meaning. Maybe a return code of 1 means that one type of error occurred, while a return code of 2 means that a different type of error occurred. If you have scripts that are executing other scripts, then you can program accordingly to these return codes if you need or want to. In this lesson, you learned that all commands return an exit status. Valid exit statuses are numbers that range from 0 to 255. An exit status of 0 represents the successful execution of a command, and a non-zero exit status represents some type of error condition. You learned about the special variable $? And how it contains the value of the exit status of the previously executed command. You made decisions using the exit status of commands by using if statements, ands, and ors. Finally, you learned how to control the exit status of your own shell scripts by using the exit command. Let's execute a command and check its exit status. We'll use ping here. I'm going to use -c, which stands for count. We'll use a count of 1, which means send 1 packet, and we'll ping google.com. We see here that 1 packet was transmitted, 1 was received. We have 0% packet loss. So to check the exit status, we'll use echo $? And you see that we do have an exit status of 0 indicating success. Let's go ahead and try another ping command. This time I'll add the W option, which allows us to specify a timeout in seconds. So I'm just going to set that to 1. I think the default timeout is something like 10 seconds, and I just don't want to wait that long. So we'll ping Amazon.com this time. We see this time we get 100% packet loss. Let's look at the return code here. $? Says the return code or exit status of that ping command is 1. Let's do something different. Let's do this. ping-c1 amazon.com.blah. This time we get an error saying that the host is unknown. Let's check the exit code again. And this time we get an exit code of 2 from the ping command. So if you were checking to see if you could ping a host in one of your scripts, you could have your script act differently based on the return code. And remember that you can typically check the various exit statuses and what they mean for a given command by looking at its man page. Let's go ahead and do that now for ping. I'll run man ping. I'm going to use a / to start a search. And then I'm just going to look for code. And then that's code point. We don't care about that. I'll hit N for next to go to the next instance of code. I'll just quickly read one sentence here. If ping does not receive any replies at all, it will exit with a code of 1. So here you can see when it exits with a code of 1, what it means, exits with a code of 2, what it means. And of course, if it's a success, it exits with a code of 0. Type Q here to get out of the man page. Let's use the double ampersand, which stands for AND. This command will attempt to create a directory, and if it succeeds, then the command following it will be executed. So we'll try make dir temp json bak. We'll use the double ampersand to indicate an AND. Then we'll use the cp command to try to copy the etc host file into that directory. You can see that the make directory returned a non-zero exit status. We'll look at that here. And since it failed, the cp command did not get executed. I'm going to modify the make dir command so that it does work. We'll use a -p to say create the parents. So we'll go ahead and do that and execute it. So now you can see that there was no error from the make dir command, and the copy command with a -v says be verbose, and it says that we copied the etc host file into the temp json back directory. Okay, this time let's try an OR command. Let's use cp-v etc hosts, and we'll say copy that to temp bak. We'll use the double pipe to represent OR. We'll run cp-v etc hosts into the temp directory. So in this example, the first copy command failed since there was no /temp/bak directory. In that instance, since it failed, it ran the command that followed the OR symbol, the double pipe. And then so etc hosts was copied into /temp. Let's see what happens when we reverse the order. So we'll do cp-v etc hosts into /temp, or cp-v etc host into /temp/bak. And then so this time, since the first copy command, copying etc host into /temp succeeded, then the second copy command was not executed because we were using the double pipe, or what's called the OR. Let's see what happens if we use a semicolon. I'm going to clear the screen real quick. Let's do ls etc linux-release. That's going to fail. That file doesn't exist. And we'll use a semicolon and the command hostname, which displays the name of the system you're working on. So even though the ls command returned an error, the hostname command was executed. With a semicolon, it doesn't matter if the first command succeeds or not. The second command will always be executed. Let's make the ls command succeed. We'll just look at etc hosts and then run the hostname command. And there you see that etc host file is displayed by ls, and then the hostname is returned. Again, both commands were executed since we're using a semicolon. With a double ampersand, double pipe, and semicolons, you can chain together multiple commands. It doesn't have to be just 2 commands. Here's an example of executing 3 commands, one after the other. We'll do ls etc hosts, hostname, and the uptime command. And you can see the first line was the return from the ls command, the second line was the output from the host command, and the third line was the output of the uptime command. In this lesson, you'll learn why and when you'll want to use functions. You'll learn how to create functions as well as how to use them. We'll talk about variables and their scope and how that applies to functions. You'll learn how to use parameters to access the arguments passed to your function. Finally, you'll learn about exit statuses and return codes. There's a concept in computer programming and application development known as DRY. DRY stands for Don't Repeat Yourself. Functions allow you to write a block of code once and use it many times. Instead of repeating several lines of code each time you need to perform a particular task, simply call the function that contains that code. This helps in reducing the length of your scripts, and it also gives you a single place to change, test, troubleshoot, and document a given task. This makes your scripts easier to maintain in the long run. Whenever you need to perform the same action multiple times in a script, that's a sign that you should probably write a function for that action. A function, again, is simply a block of reusable code that performs an action and returns an exit status or return code. A function must be defined before it is called. When you call a function, you can pass data into that function. You can access that data within your function as parameters. There are two ways to create a function in a shell script. The first way is to explicitly use the keyword function, then follow it by the function's name and then a set of parentheses. Next, you'll use an opening curly brace. The code or commands that follow will be executed when the function is called. To end or close your function, use a closing curly brace. The second way to declare a function is exactly like the first, except that you do not use the keyword function in your declaration. Everything else stays the same. To call or execute the function, simply list its name on a line in the script. After you define a function, it acts as any other command you can use in your shell script. When calling the function, do not use parentheses. You may have seen this syntax and style in other programming language, but that doesn't work in shell scripts. Simply place the name of a function on a line and it will execute that function. When you run the script, the word hello is displayed on the screen. Be aware that functions can call other functions. In this script, the hello function is declared. Next, the now function is declared. Finally, the hello function is called. When the hello function is called, it prints hello to the screen and then calls the now function, which prints the current time to the screen. You may have caught that the now function was defined after the hello function, and I said that functions had to be declared before they are used. In this example, that is exactly what has happened. Although the hello function calls the now function and the now function is below it in the script, the now function actually gets read into the script before the hello function is called. So in the order of execution, it is defined before it's used. If you were to run this script, you would find that it would throw an error stating that now wasn't found. This is because hello gets executed before the now function was declared or read into the script. And this is really the main point of scripting languages. They are not pre-compiled. In some languages, you could define a function anywhere, and the compiler would examine all of the source code first and then piece it all together for the final execution of the program. In a script, the commands and components are read from the top to the bottom. It's a best practice to place all of your functions at the top of your script. This ensures that they are all defined before they're used. Like shell scripts themselves, functions can accept parameters. Also, like shell scripts, you can access the values of those passed-in parameters using $1, $2, etc. You can even access all the parameters passed into the function using $@. The only difference here is that $0 is still the name of the script itself. So you can't access the name of the function using $0, but the good news is that you'll never really want to do that anyway. To send data to a function, supply the data after the function name. In this example, the hello function is called with one argument, JSON. This means that the contents of $1 inside the hello function are JSON. As you can guess, the output of this script is simply hello JSON. This script will loop through each of the parameters passed to the hello function and echo hello followed by the parameter. The output of this script would be 3 lines. The first line would be hello JSON. The second line would be hello Dan, and the third line would be hello Ryan. By default, all variables are global. This means that the variable and its value can be accessed anywhere in the script, including in any function. The only small catch is that the variable has to be defined before it can be used. You can't place a variable at the very end of your script and use it at the very top. The contents of the variable will be blank since it hasn't been given a value yet. This is true for functions as well. If a function uses a global variable, that variable has to be defined before the function is called. If we look at this snippet of a shell script, you'll see that the var global_var is defined before the function is called. In this case, the value of global_var can be accessed in the function. Here's an example of the opposite. Since the var global_var was defined after the function is called, it is not available in the function. If a global variable is defined within a function, it is not available outside that function until the function is called and executed. At the top of the script, the myFunction function is declared. It hasn't been executed yet, it's just declared at this point. So if we try to use the variable defined within that function without calling it first, the value of the variable will be empty. So in this example, the first echo statement will simply print a blank line. Next, the myFunction function is called. Now, a value has been assigned to the variable global_var. On the echo statement after the function call, it will print 1 because that is the value now assigned to global_var. A local variable is a variable that can only be accessed within the function in which it was declared. Use the local keyword before the variable name, and only use the local keyword the first time the variable is used. Note that the local keyword can only be used inside a function. It's a best practice to use local variables inside of your functions. However, you'll find plenty of shell scripts that do not adhere to this recommendation. Most of the times it will not cause a problem as long as you are using unique variable names throughout your script. Functions are really like shell scripts within a shell script. Just like a shell script, a function has an exit status, which is sometimes called a return code. This exit status can be explicitly set by using the return statement and following it with the status you would like to return. If no return statement is used, then the exit status of the function is the exit status of the last command executed in that function. The return statement only accepts a number, and it's only integers between 0 and 255 that can be used as an exit status. An exit status of 0 signifies the successful completion of a command or a function. A non-zero exit status indicates some type of error. To access the exit status of a function, use $? right after the function is called. In this snippet, the value of $? will be the exit status of the my_function function. You can use the exit status of a function to make a decision. For example, you could check to see if the exit status is 0. And if it is not, then you know some sort of error occurred. At that point, you could do some sort of error handling, for example. Before we wrap up, I wanted to show you an example of a function that you might actually use in one of your shell scripts. The backup_file function will create a backup of a file and place it into the temp directory. I've used this kind of function when my script modifies several files and I want to make sure I have a copy to view or even restore just in case something unexpected happens. In any case, the first line of the function checks to see whether what was passed in is, number 1, a file, and number 2, if it exists. If it is a file and it does exist, a variable called back is created. It starts off with /temp, followed by the base name of the passed in file, the current date, and the PID of this shell script. The base name command removes any leading directory components and returns just the file name. The base name of /etc/host is just host, for example. The date command is using a nice format of year followed by month and finally the day, all separated by dashes. $$ represents the PID or process ID of the currently running shell script. I use this so if I run the script multiple times on the same day, the PID will be different each time I run the script, and thus an existing backup won't be overwritten. In this snippet, the backup_file function is called with /etc/host as an argument. This will create a copy of that file and place it in the temp directory as just described. Finally, there is an if statement that examines the return code of the backup function. This is an okay function, I just kind of ran out of space on the screen, so I'll briefly talk through how we can make this better. You can also see a better example in the downloadable scripts available along with this course. One thing we can do is change the if statement to an if-else statement. If the file exists, let the exit status of the function be the exit status of the cp command. If the cp command returns a non-zero code, then our function really has also failed. If we know for a fact that the file doesn't exist, then we can use the else clause to explicitly return a non-zero exit status back to our main script. We can also use the local keyword to make the back variable local to this script. We could also improve what happens after the function is called. If we know the function and thus the backup has failed, you can exit the script with a non-zero exit status. You could also do some other sort of error handling. Maybe you don't want to exit the script, but instead just keep track of all the files that failed to get backed up. Also note that you could potentially move this bit of code into the backup file function if you wanted to as well. I'm just using this as an example to demonstrate how you can use the return code of a function to make decisions and access that data with the $? variable. In this lesson, we talked about the concept of dry, which stands for don't repeat yourself. If you find yourself writing the same bit of code in multiple places in your script, it's a sign that you should use a function. You learned how to create and use functions. You also learned that by default, all variables are global. You learned how to use the local keyword to define local variables that are only available within the function that they are defined. We talked about how to use positional parameters within your functions. Finally, we covered how to use exit statuses with your functions. You'll find a downloadable shell script checklist and template that comes along with this course. I'm going to briefly go over the main points in that checklist. First off, all scripts should start with a shebang. This is the first line of your script, and it explicitly declares which interpreter is to be used to execute the script. Next, you should include at least a one-line comment summarizing what the script does and maybe why it exists. You can include more information if you'd like. Some people like to include information such as the original author of the script, the version of the script, etc. If you're going to be using global variables in your script, they should come next unless their value cannot be determined until a later point in your script. Functions should come next. Group all of your functions together following the global variables. Within your functions, be sure to use the local keyword when defining variables that are local to the function. Following the function section, the main portion of your shell script begins. Finally, remember to explicitly use an exit status. If you do not supply an exit status, which is a number from 0 to 255, the exit status of the previously executed command will be used as the exit status of your script. It's best to control this rather than to leave it to chance. At least end your script with an exit 0 line. If your script was able to get to the last line, then in most cases that means it's successfully completed. Also keep in mind the other places where your shell script may terminate. You'll want to use exit statements there as well. For example, if your script performs some sort of check and then stops because the check failed, you'll want to exit with a non-zero exit status at that point. The next two videos will introduce you to wildcards and show you how to use them on the command line. Since shell scripts are really nothing more than a collection of command lines, this should prove to be really helpful to you. After these two videos, we'll get into specifically how to use wildcards in shell scripts. In this lesson, you'll learn what wildcards are, when you can use them, and the various types of wildcards. Finally, you'll get to look over my shoulder as I run through several examples of how to use wildcards on an actual Linux system. A wildcard is a character or a string that is used to match file and directory names. You can use wildcards to create search patterns that, when expanded, will return a list of matching files and directories. Sometimes wildcards are referred to as globs or glob patterns. Globbing is the act of expanding a wildcard into the list of matching files and directories. Wildcards can be used in conjunction with most Linux commands. If a command accepts a file or directory as an argument, then you can use a wildcard in the argument to specify a file or set of files. You'll find yourself using wildcards with commands like ls, rm, cp, mv, and others. Here are the two main wildcards. They are the asterisk and the question mark. The asterisk, or star as I like to call it, matches 0 or more characters. It matches anything. By itself, it's not really that useful, but when you combine it with other parts of file or directory names that you're looking for, it becomes powerful. For example, we could use star.txt to find all the files that end in .txt. If you wanted to list all the files that start with the letter A, then use A star. If you want to find all the files that start with an A and end in .txt, then use A star.txt. The question mark matches exactly one character. If you want to find all the files that only have one character preceding .txt, then use question mark.txt. To match all the two-letter files that begin with an A, use the letter A followed by a question mark. To match all the files that start with A and then are followed by exactly one more character and then end in .txt, use A question mark.txt. You can use something called a character class to create very specific search patterns. Start with a left bracket, then list one or more characters you want to match, and then end with a right bracket. For example, if you wanted to match a one-character long file name that was a vowel, you would use bracket A-E-I-O-U bracket. If you wanted to match files that start with CA followed by either an N or a T followed by 0 or more characters, then use CA bracket NT bracket star. This pattern will match files named can, cat, candy, and catch. If you want to exclude characters in a match, use an exclamation mark. For example, if you wanted to find all the files that do not start with a vowel, use bracket, exclamation mark, A-E-I-O-U, bracket star. Baseball and cricket match this pattern because the first character is not an A, E, I, O, or a U. When using character classes, you can create a range by separating two characters with a hyphen. If you want to match all the characters from A to G, use bracket A hyphen G bracket. If you want to match the numbers 3, 4, 5, and 6, use bracket 3 hyphen 6 bracket. Instead of creating your own ranges, you can use predefined named character classes. These named character classes represent the most commonly used ranges. Alpha matches alphabetic letters. This means it matches both lower and uppercase letters. ALNUM or ALNUM matches alphanumeric characters. This means it matches alpha and digits. Said another way, it matches any uppercase or lowercase letters or any decimal digits. Digit represents the numbers in decimal from 0 to 9. Lower matches any lowercase letters. Space matches white space. This means characters such as spaces, tabs, and newline characters. Upper only matches uppercase letters. What if you want to match one of the wildcard characters? Then you would escape that character with a backslash. To escape the wildcard, simply place the backslash before the wildcard character. If you want to make your life easier, don't name your files with question marks and asterisks. However, you may end up receiving a file with these characters in them, so you'll need to know how to handle them. For example, if you wanted to match all the files that end with a question mark, then use star backslash question mark. An example match would be a file named DONE question mark. Let's do an ls to get our bearings and see what files and directories we're working with. Let's use the asterisk or star and match all the files that end in .txt. lsstar.txt. What just happened is the shell performed a globbing operation to expand star.txt, and it passed those results to the ls command. In this example, running lsstar.txt is the same as running ls ab.txt, a.txt, b.txt, and songs.txt. Of course, you can clearly see it's easier to use a pattern like star.txt than it is to type out all the files by hand. I just wanted to be clear about what is happening when you use wildcards. Now, let's look at all the files that start with the letter A. How would you do that? That's right, type in ls a star. Now let's find all the files that start with an A and end in .txt. We can do that by typing in lsa star.txt. Can you see a way that we can make the wildcard even simpler? How about this? lsa star t. And that gives us the same results. Let me clear the screen here and reset our bearings. Look at what we're working with. Now let's use the question mark wildcard. Let's match all the files that are exactly 1 character in length. We'll do that by running ls question mark. If you want to display all the files that are 2 characters in length, then just use 2 question marks. Each question mark represents a single character. So we'll do question mark, and we'll see that all the 2 character files and directories are returned. In this case, they're just files. Let's list all the files that start with an A, then contain exactly 1 character and end in .txt. To do that, we'll run lsa followed by a question mark, which represents exactly 1 character, and then .txt. Let's check out the difference between the question mark and star. Let's run lsa star.txt. The star matches 0 or more characters, so running lsa star.txt matches the file named a.txt. Before we continue, I want to point out that you can use the same flags and options as you normally do with a command while you're using wildcards. Let's get a long listing of all the files that start with the letter A. So just like we normally would use with ls to get a long listing, we'll use -l, and then we'll use a star to get every file and directory that begin with the letter A. Go ahead and clear the screen again here. Here's an example of using a character class. Let's match all the files that start with the letter C, then contain a vowel and end in T. To do this, we'll run ls c bracket, and then any of the characters, or excuse me, all the characters we want to match with A, E, I, O, U, and then T. And I want to point out too that it doesn't matter what order the characters appear in the bracket. So we can use E, I, O, A, U, and we'll get the same results. Let's do another one here. Still get the same results. Let's use a range. This range will match all the files that start with an A, B, C, or D. To do that, we'll do ls bracket A-D to represent A through D, and then star. Here's an example of using a named character class. This command will return a list of files that end in a digit. I've simply been using the ls command to demonstrate how to match files using wildcards, but let's do a little bit of actual work with wildcards. Let's clear our screen and run ls again to see what's in our directory. Let's move all of the text files into the directory named notes. To do this, we can use the mv command to move, and then we'll use star.text to match all the text files, and we'll end with the directory name, which is notes. And let's see if that worked. Okay, I'm not seeing any of the files that end in .txt. Let's look in the notes directory and see if they're there. And indeed they are. Let's move all of the MP3 files into the music directory. We can do this in a couple of different ways. One way would be to run mv star.mp3 and specify the songs directory. We can also use star3 since that would match, and we can even use a character class like star and then digit. I'll go ahead and just use mv star.mp3 to perform the match. Let's look inside the music directory, and we can see that the 2 MP3 files that matched our star.mp3 expression are moved into the music directory. Let's use wildcards to delete some files. Here's a good pattern to follow. Test your wildcard pattern with the ls command before you use that pattern with the rm command. This way you can hopefully avoid deleting any files that you do not intend to remove. Let's remove all the files that are 2 characters in length. We'll check our wildcard pattern here to make sure it returns what we want to do. And it looks like it does, so we'll go ahead and run rm using that same expression. And now the files that match that pattern are gone. Today you learned how to use wildcards. You learned that the asterisk matches 0 or more characters. You also learned that the question mark matches exactly 1 of any character. You learned about character classes and how you can match any character that is included between the brackets. You were taught about ranges and how you can create your own custom ranges by starting with a character, following it by a hyphen, and then ending it with another character. Finally, you learned about the various named character classes and how they can be used to match common sets of characters, such as digits, uppercase letters, and lowercase letters. In this video, you'll learn how to use wildcards in your shell scripts. You'll run into situations where you'll want to work on a group of files or directories. To do that in a script, you can use wildcards. This is very similar to the process of using wildcards at the command line. You can use wildcards just as you did on the command line. This script, for example, changes to the var www directory and copies all of the HTML files into var www-just-html. Let's say you want to do something for each file that matches a wildcard. In that case, you can use a for loop. Let's use a for loop to perform an action on all the HTML files in a directory. This script simply echoes to the screen the name of the file that is about to be copied and then copies that file from the var www directory into the var www-just-html directory. Of course, you could do something more complex in this loop if you wanted to or needed to. Notice that the wildcard expression is being used where you would normally provide a list. This wildcard expression will expand to create a list of matching files and directories. In the case that the wildcard is not matched, the for loop is just simply not executed. Also notice that we explicitly changed into a directory before we used the wildcard. The output of this script might look something like this: copying about.html, copying contact.html, and finally copying index.html. Let's modify the script just slightly. Instead of cding into the var www directory, let's include that path in the wildcard expression. You can see the wildcard expression is /var/www/star.html. The output of this script will look something like this: copying var www about.html, and then the same thing for var www contact.html and /var/www/index.html. Notice how the path is included in the output. This is because we included the path in the wildcard expression. Here's an example of how not to use a wildcard. In this script, all the files in the current working directory that match star.html will be copied into /var/www-just-html. The current working directory is the directory from which you started this script. If you wanted to get the same results as the previous scripts, you would have to cd into /var/www before you executed this script. Instead of having this dependency live outside of your shell script, you should instead explicitly cd into the desired directory with a cd command within your shell script, or include the path in the wildcard expression. In this lesson, you learn how to use wildcards in your shell scripts, just like you can on the command line. We also looked at how you can use wildcards in conjunction with loops. Finally, you learned that if you do not supply a directory in the wildcard expression or cd into a directory before the wildcard expression is used, the wildcard expression will operate on the contents of your current directory. Let's take a look at this relatively simple script here. It's called copy www.sh. And you can see that it changes directory into var www and then copies all of the files that end in HTML to var www-just-html. Let's go ahead and look at what's in var www now. And let's also see what's in this other directory. So there's nothing in the just HTML directory. So when we execute this script, we'll expect everything in the var www directory except for style.css to end up in the var www-just-html directory. Let's go ahead and run the script and let's see if that happens. Okay, it says it's copied about.html, contact.html, and index.html. I'll just look in this directory and we can see that indeed those files were copied over, and style.css was not copied because it didn't match the wildcard expression star.html. Let's remove the files in this directory. Make sure they're gone, and let's change the script just slightly. So instead of changing the directory to var www, let's go ahead and place that path in the expression itself. Okay, again, we'll just look at what's in this directory. There's nothing there at the moment. And those are the files that are in var www. We'll execute this script. And this time you can see that the path was included in the output here, /var/www/about.html, for example. And you can see again that those files did indeed get copied over there. I removed those files in that directory. Let's do one other thing here. Let's edit the script. And this time we're going to remove the path. And we're not going to include a cd directive here or a cd command. So this is going to copy all the HTML files from the present working directory or the current working directory into that var www-just-html directory. Okay, we can see that there are no HTML files in this directory, our present working directory. Let's just go ahead and create one. We'll use the touch command to create an empty file. And we'll just name this file test.html. And we'll go ahead and run this newly modified script. And you can see that it says copying test.html. Now that's okay if that's what you wanted, but if you really wanted the files to be copied from var www, what you would have to do would be to cd to that first and then run that script. So we'll go ahead and do that now. Well, before we do that, let me just show you what's in var www-just-html at the moment. And you can see that that test.html file is there. Let's go ahead and run this script again from the var www directory. And this time we'll just give the full path to the script. And then you can see that it acts as the first couple of times where we ran the script, where it copied the contents of this directory into the var www-just-html directory. So this is just a minor thing to keep in mind. So either explicitly change directory before you use a wildcard, or include the path in the wildcard. If you don't do either one of these things, then the wildcard will operate on whatever present working directory you're currently in. In this lesson, you will learn when to use the case statement and how to do it. You already know how to make decisions and vary the flow of your scripts by using if statements. If you find yourself using an if statement to compare the same variable against different values, you could use a case statement in its place. Some people argue that for these situations, a case statement is easier to read. In any case, you'll see case statements in shell scripts, and you'll want to at least understand what they are doing and how they work. One common place to find case statements in use is in system startup scripts, for example. To create a case statement, start with the word case, follow it with an expression, which is most commonly a variable, and end the line with the word in. Next, you list a pattern or a value you want to test against the variable. End the pattern with a parentheses. If the pattern is matched, the commands following it will be executed. The execution will stop when a double semicolon is reached, and the script will continue after the case statement. You can test for multiple values using the same pattern. Finally, the case statement is ended with ESAC, which is case spelled backwards. Here's an example case statement. You'll find something similar to this in startup scripts or scripts that are used to control the behavior of a program. The case statement examines the value of $1. Remember that $1 is the first argument supplied to the shell script. If $1 is equal to start, then user sbin sshd is executed. If $1 is equal to stop, then the kill command is executed. If $1 doesn't match start or stop, then nothing happens and the shell script continues after the case statement. Note that the patterns are case sensitive. If someone were to execute this shell script and use start in all capital letters as the first argument, nothing would happen. The case statement only matches start in all lowercase letters and stop in all lowercase letters. Here's a slightly modified version of the case statement. In this example, a wildcard is used. An asterisk, or star as I like to call it, matches anything. Wildcards are covered more in depth in another section of this course. What you learn about pattern matching there applies to case statements as well. In this example, anything other than start and stop will cause the last pattern to be matched. In that case, the echo and exit commands will be executed. I used a semicolon here to separate the commands so that they would fit on the screen, but you could have just as well placed them on separate lines. This is yet another slightly modified version of the same case statement. This time you might notice that a pipe was used. You can use the pipe as an OR. So if $1 is equal to start in all lowercase or start in all uppercase, the SSHD command is executed. We did the same thing with stop. And like the previous example, the wildcard will act as a catch-all and match anything else. Here's an example where you are asking for input from the user. This input is stored in the variable answer. Even though you may ask the user to enter a lowercase y or a lowercase n, they may do something slightly different. Instead of being so strict, you can adjust the pattern matching in your case statement. Like I said earlier, all the rules for wildcards are in play for the matching section of the case statement. Here we are going to use character classes. As a quick reminder, character classes are simply a list of characters between brackets. A character class matches exactly one character, and a match occurs for any of the characters included between the brackets. The first character class in this example is lowercase y and uppercase y. So if the user entered a lowercase or an uppercase y, the first pattern will match, and then you answered yes will be echoed to the screen. Also, if the user entered YES using any combination of upper or lowercase letters, the pattern following the pipe will match, and you answered yes will be echoed to the screen. That pattern is 3 characters in length and is comprised of 3 character classes. The first character class is a lowercase and uppercase y. The second is a lowercase e and uppercase e. And the third character class is a lowercase s and an uppercase s. We use the exact same concept to match for n or no as an answer. The last pattern is a star, so it will match anything that did not match the above patterns. You don't have to use the star wildcard by itself. In this example, the first pattern will match anything that starts with a lowercase or uppercase y. This will include answers like y, yes, or even yup. In this lesson, you learned what case statements are used for and how to create them. If you find yourself using an if statement to compare the same variable against different values, you can use a case statement in its place. You learned how to create patterns using wildcards. You also learned how to execute the same block of code from multiple values by separating the patterns with a pipe. In this lesson, you will learn why you may want to use logging in your shell scripts. You'll also learn about the syslog standard and how to generate messages that conform to that standard. Finally, you'll learn how to create your own custom logging functions. If you want to keep a record of what occurred during an execution of a shell script, you'll want to employ some sort of logging mechanism. Logs can store any type of information you want, but they typically answer who, what, when, where, and why something occurred. Logs can be useful when your shell script performs several actions or produces a lot of output that might scroll off your screen. Also, if you plan to run your shell script unattended via cron or some other means, you might want a way to look back and see exactly what happened and when it happened during a previous run. The Linux operating system uses the syslog standard for message logging. This allows programs and applications to generate messages that can be captured, processed, and stored by the system logger. It eliminates the need for each and every application having to implement a logging mechanism. This means that we can take advantage of this logging system in our shell scripts. Before we start using it, let's briefly talk about how it works. The syslog standard uses facilities and severities to categorize messages. Each message is labeled with a facility code and a severity level. The various combinations of facilities and severities can be used to determine how a message is handled. Facilities are used to indicate what type of program or what part of the system the message originated from. For example, messages that are labeled with a kern facility originate from the Linux kernel. Messages that are labeled with a mail facility come from applications involved in handling mail. There are several facilities. If your script is involved in handling mail, you could use the mail facility for logging. If it's not clear what facility to use, you can simply use the user facility. Also, the facilities ranging from local 0 to local 7 are to be used to create custom logs. These facilities would also be appropriate for custom written shell scripts. The severities are emergency, alert, critical, error, warning, notice, info, and debug. The most severe message is an emergency message, and the least severe message is a debugging message. These combinations of facilities and severities are used by the system logger to handle these messages. Most messages are simply written to a file. Each distribution uses a slightly different set of defaults, and these logging rules are configurable and can be changed. You'll find many messages stored in var log messages on some distributions, while others use var log syslog, for example. You'll have to consult the documentation for the system logger that is in use on your system. It's typically one of syslogd, rsyslog, or syslog-ng, although there are several other possibilities. Okay, now that you know about the standard logging system that is in play, you can take advantage of this in your shell scripts by using the logger command. The logger command generates syslog messages. In its simplest form, you simply supply a message to the logger utility. By default, the logger utility creates messages using the user facility and the notice severity. If you want to specify the facility and severity, use the -p option followed by the facility, then a period, and then the severity. So, to use the local 0 facility and the info severity, you would run logger space -p local.info and then follow that with the message you want to generate. If you want to tag your message, use the -t option. Typically, you'll want to use the name of your script as the tag. This way, you can search for the name of your script in a log file to extract just the messages for your script. If you want to include the PID or process ID in the log message, use the -i option. Let's look at the messages generated by these logger commands. The first logger command is used without any options. You can see that it generates a message with a timestamp and includes the message passed to the logger command. This message will be routed based on the system logger configuration. For most distributions, this message will end up in the var log messages file or the var log syslog file. The next logger command generates the same message, but this time we have specified the facility and severity. Remember that different facilities and severities can cause the system logger to route the messages to a different log file. If you want to display the message to the screen in addition to sending it to the logging system, use the -S option. The first logger command on your screen uses a tag. The message that it generates now contains the specified tag. The other logging command uses the -I option, which causes the PID to be included in brackets in the log message. If multiple copies of your script can run at the same time, then having a PID can help differentiate the logs being generated by one instance of the script versus logs being generated by another instance of the script. You can even create a function in your shell script to handle logging. Here's an example from one of my scripts. This function, named logit, expects that a log level be passed into it followed by a message. It assigns the first thing passed into it to the log_level variable. Next, shift is run to shift the positional parameters to the left. This means that the special variable $@ contains everything but the first positional parameter, which we already use for our log_level variable. Everything that is left over is assigned to the MSG variable. Next, a timestamp variable is created and assigned some output from the date command. If the log level variable is set to error or the verbose global variable is set to true, then a message is echoed to the screen which includes information such as the timestamp, the log level, and of course the message. Instead of using echo, this function could have employed the use of the logger command if we wanted to do that. Here are some examples of calling this function. The first time it's called, the info log level is used and the message is processing data. If the command fetch data host fails, then the logit function is called with an error log level and a message that states could not fetch data from host. The fetch data command in this example is made up. It could be another shell script, for example. But in any case, this gives you an idea of how you can use a custom written logging function. In this lesson, you learned why you may want to use logging in your shell scripts. You also learned about the syslog standard and how to generate messages with the logger utility that take advantage of this standard. Finally, you learned how to create and use your very own custom logging functions. In this lesson, you'll be introduced to while loops. We'll talk about how and when to create infinite while loops. Next, you'll learn about different ways to control the number of times a loop is performed. You'll learn how to limit the number of loops, how to end a loop based on user input, and how to end a loop based on the exit status of a given command. I'll show you one of the most common use cases for a while loop, which is to read a file one line at a time. Finally, you'll learn how to use the break and continue statements to selectively operate on items in a loop. A while loop is a loop that repeats a series of commands for as long as a given condition is true. This condition could be some sort of test, such as checking to see if a variable is a certain value or checking to see if a file exists, for example. The condition could also be any command. If the command succeeds and returns a 0 exit status, then the while loop will continue. When the command fails and returns a non-zero exit status, the condition is false and the while loop stops. If the condition is never true, then the commands inside the while loop are never executed. Typically, the while loop checks for a condition that will be changed by the commands inside the while loop. If the condition is examining the value of a variable, that variable will be manipulated and changed in some way by the commands inside the while loop. If the condition is checking the exit status of a command, then the commands in the while loop will eventually cause the exit status of that command to be non-zero or false. If the condition that is being tested always returns true, then the while loop will never exit. If this happens, you'll need to interrupt the script by hitting Ctrl+C if you're running it interactively from the command line. Otherwise, you'll need to use the kill command to kill the process. Typically, when this happens, it's due to a bug and logic error in the script. There may be cases where you want an infinite loop. If so, you can simply make the condition always return true by using the true command. The true command always exits with a 0 exit status and thus is always true. If you want to create some type of service or daemon, you can use this technique. You would simply start your shell script in the background and it would continually run until it was killed. When you do this, there are typically a series of commands in the while loop and then a sleep command to pause the execution of the script for a given number of seconds. Let's take a look at a couple of actual examples of while loops. One thing you can do with while loops is control the number of times it loops. One common pattern you'll see is to create an index variable, check the value of that variable, then increment that variable at the end of the command section of the while loop. This example demonstrates one way to loop 5 times. First, index is set to 1. The commands in the while loop get executed because index is less than 6. The echo command is executed and displays creating project-1. Then the makedir command is executed. Finally, the index variable is incremented by 1. This is done by using something called arithmetic expansion. You can enclose a mathematical expression inside double parentheses. The double plus sign is the increment operator and it simply adds 1 to the variable it follows. The first time this loop is executed, index will be incremented from 1 to 2. The next iteration of the loop continues because index, or 2, is less than 6. This repeats until index is set to 6 on the 5th loop. 6 is not less than 6, so the while loop is complete and the script will continue. Here is the output of the previous script. As you can see, it completed the loop 5 times. Here is an example where user input populates the variable that is being used to control the while loop. Here we are asking a user for a name. The first read command populates the name variable with the user's input. The next read command displays back what they entered and asks them if it's correct. That input is stored in the correct variable. If the user answers anything other than a lowercase y to that question, the loop repeats. When the correct variable is set to lowercase y, the loop is complete and the script continues after the while loop. Here's what running this script would look like. The first time the loop executes, something other than y was entered, so it repeats the loop. Once y is entered, the loop exits. Let's look at an example where you need to check the return code of a command. Let's say you have a script that runs on a database server and performs some sort of maintenance or backup. Let's make that script wait until the application server is off the network before it continues. This way we can know that the application is not actively using the database while we are performing our maintenance. We do this by using the ping command. Using -c1 causes a count of 1 packet to be sent to the server. We also redirect the output to dev null since we don't really need to see the output. If the ping command succeeds, then an exit status of 0 is returned. If it fails, then a non-zero exit status is returned. While the server is pingable, the condition is true and the loop continues. Once the ping command fails, the script continues. Here's some sample output from the previous script. While the server is pingable, the loop continues. Once it can't be pinged, the loop exits and the script continues. If you've ever tried to use a for loop to read a file line by line, you'll quickly find that it doesn't work. What happens in that situation is the for loop will read the file word by word. To actually read a file line by line, use while in conjunction with the read command. On the last line of the while loop, use the keyword done, followed by the less than sign, followed by the file you wish to read. This example loops through the etc/fstab file line by line, printing the line number followed by the actual line. We use a variable to keep track of the line numbers and increment it as we loop through the file. Here is some sample output from running that script. You'll see the line number followed by the actual contents of the line from the etc/fstab. In this example, the fstab is 5 lines long. You can also read from the output of a command instead of a file. To do this, pipe the output of the command into the while loop. Let's modify the previous example to only print out lines that contain XFS file systems. We use grep, XFS, etc/fstab to extract the lines and then pipe those lines to the while loop. We simply prepend each line with XFS : followed by a space and then following it with the actual line from the fstab. Here's what that would look like using the same fstab file from the previous example. In the previous examples, we've been using the read command to read the entire line into one variable. However, the read command supports splitting the data it reads into multiple variables. Each variable supplied to the read command will store one word or one field of data, with any leftover words or fields assigned to the last variable supplied to the read command. Let's modify the previous example a bit. Here we're going to assign the first word of data to the fs variable, the second word to the mp variable, and the rest of the line to the rest variable. If you want to assign each field in the fs tab its own variable, you can do that too. Here I was just going to use the first two fields, and that's why I chose to use 3 variables. This is the output of the script. You can see that the CentOS root file system gets mounted on /, while the file system labeled boot gets mounted on /boot. If you want to exit a loop before its normal ending, use the break statement. The break statement exits the loop, but it does not exit the script. The script will continue after the loop. Here is one way you could create a simple menu. This example creates an infinite loop using while true. Next, it asks the user for some input and stores that input in the variable choice. A case statement is used to determine what action to take based on the user's input. If 1 was entered, then the df command is executed and the loop repeats, asking the user for input again. If 2 is entered, then the uptime command is executed and the loop repeats. If anything other than 1 or 2 is entered, then the break statement is executed, which ends the while loop. Note that the break statement can be used with other kinds of loops, like for loops, for example. If you want to restart the loop at the next iteration before the loop completes, use the continue statement. Any commands that follow the continue statement in the loop will not be executed. Execution continues back at the top of the loop, and the while condition is examined again. In this example, we loop through a list of MySQL databases. The -B option to MySQL disables the ASCII table output that MySQL normally displays. The -N option suppresses the column names in the output. This prevents the header from being displayed. Finally, the -E option causes MySQL to execute the commands that follow it. Ultimately, this MySQL command lists one database per line of output. That output is piped into a while loop. The read command assigns the input to the db variable. First, we check to see if the database has been backed up recently. This is a command that I made up. Perhaps it could be a call to another script. In this contrived example, the db backup recently script returns 0 if the database passed to it has been backed up in the last 24 hours. Otherwise, it returns a 1. We use an if statement to examine the return code of that script. If the database has been backed up recently, we call the continue statement, which starts the loop over again. The next database is checked, and the next one, and so on. If the database has not been backed up recently, then we go ahead and create a backup of it. Again, the backup command is something that I made up. It could be another script that actually performs the backup, for example. The main point in this example is to demonstrate the use of the continue statement. Here we avoid unnecessary work by selectively operating on the items in the while loop by using the continue statement. Like the break statement, the continue statement can be used with other types of loops. In this lesson, you learned about while loops. We talked about creating infinite loops by forcing the condition of the while loop to always be true. Next, you learned about controlling loops by counting the number of times a loop has executed, by examining user input, and by checking the exit status of a command. You also learned how to use the read statement in conjunction with while loops to read files line by line. You even learned how to assign multiple values to multiple variables at once using the read command. Finally, you learned how to further control loops with the break and continue statements. In this lesson, you will learn about the options built into Bash that will help you find and fix errors in your shell scripts. A software bug is an error in a computer program that causes it to produce an unexpected or incorrect result. Most of the bugs are actually mistakes in the program's code or in its design. If you encounter a bug or an error in one of your scripts, you'll want to see exactly what is happening during the execution of that script. Maybe something isn't working as you initially anticipated, and you want to figure out where things are going wrong and how you can update your script so that it performs as expected. Sometimes your script will produce an incorrect result or behave in unintended ways. Sometimes it will simply stop because of a syntax error or a typo. This process of finding errors in your script or fixing unexpected behaviors is called debugging. The Bash shell provides some options that can help you in debugging your scripts. You can use these options by updating the first line in your script to include one or more of these options. The most popular of these options is the -x option. The -x option prints commands and their arguments as they are executed. This means that instead of variables being displayed, the values of those variables are displayed. The same thing goes for expansions. Wildcards aren't displayed, but what they expand to is displayed. You'll sometimes hear this type of debugging called print debugging, tracing, or an xtrace. If you are using this option in a shell script, simply add -x to the end of the shebang line. If you want to do this at the command line, run set space -x. Use set space +x to stop this debugging behavior. You can also use this option for just a portion of your script. Just before you want to start displaying the commands to the screen, add a set -x line. Place set +x on a line after the section of the shell script that you're debugging. Again, set space -x will start the xtrace while set space +x will stop the xtrace. Here's a very simple example that demonstrates the use of the -x option. You can see that -x has been added to the end of the shebang. At the bottom of the screen is the output you'll see when you run this script. You'll notice that there are lines that start with a plus sign. Those are the commands that are being executed from the script. In this example, there are two commands that are executed. The first is setting the value of the test_var variable. The second command is to echo that value to the screen. In the output, the result of the echo command, which is test, is displayed. There is no plus sign in front of it because it is output as a result of a command and not a command itself. Here's another example. This shows how you can turn debugging on for just a portion of your script. First, the test_var variable is set. You'll see in the output that nothing is listed for this command because debugging isn't on at this point. The next line turns on debugging with a set -x command. Again, nothing is displayed in the output for this action. Now the test_var is echoed to the screen. The echo command is displayed because debugging is now on. Of course, the output of the echo command is displayed next on the screen. We use set +x to turn off debugging. That set command is displayed on the screen. Finally, the hostname command is executed and only its output is displayed. Again, this is to demonstrate how you can encapsulate a block of code with set -x and set +x to debug that particular section of code. You can do the exact same thing with the other options that we'll be covering next. Another useful option that can help you in finding errors in your scripts is the -e option. It causes your script to exit immediately if a command exits with a non-zero exit status. Remember that an exit status of 0 indicates the successful completion of a command, and any exit status other than 0 indicates some sort of error. This can really help you pinpoint exactly where the problem is. You can use this in combination with other options, including the -x option. When used as an argument to the bash command, these options act like any other options for other commands. Options that do not take arguments can be combined, and only one hyphen is required, followed by the options. Also, it doesn't matter in which order they're used, so we can use -ex or -xe. If you want, you can use a hyphen before each option, but this is unconventional. Here is an example using the -e option. First, a value is assigned to the variable file_name. Next, the ls command is executed using file_name as an argument. Finally, the contents of the file_name variable are displayed to the screen. However, when you execute this script, the ls command returns a non-zero exit status since the file doesn't exist. Because the -e option was used, the execution of the program halts and the echo command is never attempted. This time we'll use both the E and X options. The X option causes the commands to be displayed on the screen. First, it displays the creation of the file_name variable. Next, it displays the ls command. You can clearly see what ls is doing in this example. It's trying to display information about a file named /not/here. Of course, this causes an error and the script stops because of the -e option. Yet another useful option that can help you in the debugging process is the -v option. It prints the shell commands just like they are read in from the script. -v prints everything before any substitutions and expansions are applied. The -x option performs variable and wildcard expansion, but the -v option does not. You can use them in combination to see what a line looks like before and after substitutions and expansions occur. Here's an example of the -v option. It causes every line of the script to be displayed to the screen before it's executed. You'll notice that the lines are exactly as they are in the shell script. In this script, the only thing that happens is that test gets echoed to the screen. Here's what would happen if we added the X option to the previous script. What's useful about this output is that we can see how a command looks in the shell script and how it actually gets executed. Take the echo command, for example. We can see in the script that we run echo $test_var, and that actually causes echo test to be executed. From the command line using a bash shell, you can run help set. This will display information about the options we covered in this lesson, plus other options that are available. You might want to pipe this output to a pager like less so you can easily scroll through all the options and their descriptions. In this lesson, you learned how to use a few different built-in bash options to aid you in debugging shell scripts. You learned about the -x option, which prints commands as they will be executed. You learned how to exit your script if it encounters an error by using the -e option. Finally, you learned how to display the commands in your shell script exactly as they appear by using the -v option. In this lesson, you will learn how to use variables to control the behavior of your shell scripts and help you in debugging. You'll also learn how to manually debug a script. We'll also talk about syntax highlighting and how that can help you avoid common mistakes. You'll learn about a special bash variable that you can use to give you valuable information about what is happening inside of your scripts. Finally, you'll learn about the differences between Windows and Linux file types and the problems you may encounter if you plan to use multiple operating systems to create scripts. Many times using -x, -e, and -v is sufficient, but if you want a bit more control around debugging, you can create your own code to do it. One method I personally use is to create a variable called debug. I set this to true if I'm currently debugging or false if I'm not. I'm using the bash built-in booleans of true and false. If you want to use a boolean, do not quote them. If you were to quote true, for example, then it will act as a string. That's fine, and that's one way to do it, but then you'll have to use string comparisons later on in your script. Using boolean simplifies testing for the debug condition in your script. Here is a simple example of using a debug variable with a boolean value. You can test if debug is set to true by using an if statement. Since debug is true, the if statement is true and echo debug mode on is executed. If you were to set debug equals to false, then the if statement would be false and the else block would be executed. You can use a debug variable in conjunction with ands or ors. Remember that the double ampersand means and. It will only allow commands to be executed after it if the return code of the preceding command was 0. The true boolean always returns a 0 exit status. So for the first example, debug is set to true. Since that is a 0 exit status, the echo debug mode on command is executed. You can use this pattern to execute certain commands when debug is set to true. The double pipe symbol represents OR. If the command preceding an OR returns a non-zero exit status, then the command following the OR will be executed. The false boolean always returns a non-zero exit status. So for the second example, debug is set to false. Since that is a non-zero exit status, the echo debug mode off command is executed. You can use this type of pattern to skip the execution of certain commands when debug is set to true. If debug succeeds, then what follows the OR will not be executed. This can prove to be useful when you are in the process of writing a shell script. You may not want or need to execute some commands that will repeat work already performed or take a long time to run, for example. This can speed up the creation of your new scripts, so it's good for debugging and writing scripts. Another thing you can do is set the value of the debug variable to echo. Next, place $debug before each line in your script. If debug is set to echo, then whatever would normally have been executed is simply echoed to the screen. In the first example, the output to the screen is simply ls because what gets executed is actually echo ls. In the second example, the debug line has been commented out. This causes the value of debug to be nothing. That leaves the remainder of the line, which is a space followed by ls. That means the ls command will execute. Again, this is another simple way to turn debugging on and off in your scripts. You can even create your own debug function and add whatever you would like around each command, or choose not to execute the command if you wish. Use the special variable $@ inside your function to access everything passed to the function. In this example, the command that will be executed is simply echoed to the screen, and then it executes that command. Of course, you could do something more complicated and useful. Maybe you could write this information to a log file and include timestamps showing exactly when each command was executed. Sometimes I simply open up a second terminal window and go through the shell script one line at a time. I will copy and paste the first line, then the second, one at a time on the command line until I find where the problem is. Remember that you can use this in conjunction with set-x or any other option you might think will be helpful. Many times bugs or errors in a shell script are due to a simple syntax error. Maybe you mistyped something, or you forgot to include a closing bracket or closing quote, for example. These simple mistakes can be caught before you even try to execute your script if you're using an editor with syntax highlighting. Two of the most commonly used editors on a Linux system are Vim and Emacs. By default, they both have syntax highlighting. I've included a couple of screenshots from those editors to show you what this looks like. Of course, there are plenty of other editors with highlighting support. You'll have to check the documentation for your particular editor to see if shell script highlighting is supported, and if so, how to enable it. You may be familiar with the PS1 environment variable. It controls what is displayed as your command prompt. There are other variables similar to this one. The one that is valuable for shell script debugging is PS4. PS4 is expanded and displayed before each command during an execution trace. That means that when you're using the set-x or the -x option for your bash script, the contents of PS4 are printed to the screen. By default, this is just the plus sign. However, we can explicitly set the PS4 variable. Bash includes several built-in variables such as bash_source, which is the name of the script itself, line no, which is the line number of the script, etc. Here is an example of using the PS4 variable. This script sets PS4 to the plus sign, then a space, then the name of the script by using the built-in variable bash_source. Next, we include another space followed by a colon and yet another space. Finally, we display the line number with a line no variable, use a space, a colon, and finally another space. You can see that when the script gets executed, the output changes after the PS4 variable is set. This can make the output clearer. For example, if we had a problem with the echo command, we know we can edit the script and head straight for line 4. Here's a more advanced example. It just includes more information such as the function name. I included one line of sample output here. That output is line 4 from inside the debug function. You can see how the PS4 variable allowed us to print the function name using the built-in variable funcName. Plain text files, like we are working with for shell scripts, contain a control character to represent the end of a line. For Unix and Linux systems, the control character representing a new line is a line feed. DOS or Windows systems actually use two characters to represent a new line, a carriage return and a line feed. If you've ever created a text file on a Linux system and sent it to someone that is using a Windows system, it may very well display as one long line on their computer. This is due to the lack of carriage returns. If you were to do the opposite, say create a text file on a Windows system and open it on a Linux system, there will be additional characters, specifically carriage returns, in that file. The problem in this situation is that when you display the contents of the file to the screen, you will not see the additional carriage returns. For example, if you ran cat script.sh and that file had carriage returns in it, you wouldn't see them. You would have to run cat -v script.sh to display non-printable characters like carriage returns. Carriage returns are represented by the caret symbol followed by an uppercase M. If you were to execute a file that contains carriage returns, you'll probably run into an error like this: /bin/bash -m, no such file or directory. The carriage return is being treated as part of the file name. In order to get this script to run, we need to remove the carriage returns. This situation is another reason why you should always start your scripts with a shebang. If you didn't have the shebang line, the commands would be executed using your current shell. This can lead to some strange things happening. The script might work as expected for parts of it, but totally fail at other parts due to carriage returns. If you start getting strange errors that make no sense, check to see if there are any carriage returns in your script. In addition to using the cat-v command to see if there are any carriage returns in a file, you can use the file command. If it finds the additional carriage returns, it will alert you to that fact. To easily remove these characters, I recommend that you use the DOS to Unix utility. It may not be installed by default on your system, so you may have to manually install it if you need it. This little utility converts a DOS file, or a file with carriage returns, into a Unix file, or a file without carriage returns. There is another utility which does the exact opposite, and it's called Unix to DOS. After you run the DOS to Unix command against your file, you'll find that the carriage returns are removed. You can confirm this by running the file command against the file. You'll notice that there are no warnings about CRLF line terminators. The common ways you end up with these unwanted carriage returns in your shell scripts is due to creating files on a Windows system and uploading those files to a Linux system. If you want to create shell scripts on a Windows system, see if your editor supports Unix-style line endings. If it does support this option, simply turn it on. Also, some editors can convert between DOS and Unix-style file types. You can also end up with unwanted characters in your shell scripts if you copy some text from your Windows computer and paste it into your PuTTY window. Even if you're using an all Linux system, the copy and paste action can still get you. For example, if you copy some text from a web page that has carriage returns and then paste that into a text file, that file may contain those carriage returns. In this lesson, you learned how to use variables to assist you in debugging and creating shell scripts. You also learned that it can be easier to catch mistakes if you're using an editor with syntax highlighting enabled.
You learned about the PS4 variable and how to use that in conjunction with an X-trace. Finally, you learned about the challenges of switching back and forth between Windows and Linux, and more importantly, how to catch and correct errors caused by carriage returns. In this lesson, you'll learn how to use the most important features of the sed command. Sed stands for Stream Editor, and it's used for, well, editing streams. You might not be familiar with the term stream, but if you performed any I/O redirection or piping, you've been using streams. You can think of a stream as the data that travels from one process to another through a pipe, or from one file to another as a redirect, or from one device to another. So you can think of standard input as the standard input stream, standard output as the standard output stream, and standard error as the standard error stream. By the way, these data streams are typically textual data. transformations on an input stream. For example, you can use sed to substitute some text for other text, remove lines, append text after given lines, and insert text before certain lines. Sed differs from other editors such as Vim, Emacs, and Nano in that it's used programmatically. Of course, you can substitute some text for other text, remove lines, append text after given lines, and insert text before certain lines using Vim, but that requires interaction from a human. Sure, you can write macros to perform these functions in Vim, but you have to have someone to start Vim and then execute the macros. With Sed, you can programmatically perform these edits without the need of interaction. And this makes Sed ideal to be used in shell scripts, for example. The most common use of Sed is to act as a command line version of find and replace. I'm going to use this particular application of Sed to teach you the basics of the Sed command. Notice that I said Sed command. Sed is a standalone utility and not a shell built-in. We can prove this by using the type shell built-in. So you can see that when you type sed and press enter, the user bin sed program will be executed. Of course, for standalone commands, you can use man to get help and documentation on how to use that command. So let's quickly look at sed's man page. As we've already mentioned, sed is a stream editor. The man page says it's used for filtering and transforming text. If we look at the synopsis section of the man page, we can see that we can execute sed with 0 or more options, followed by a sed script, and optionally followed by 1 or more input files. So let's exit out of this man page by typing Q and get to our first sed command. Let's create a file to work with real quick. Let's do this. Let's make sure our contents made it in the file. I'm sure it did, but let's just prove it here by catting that file. So sure enough, it says Dwight is the assistant regional manager, and that's the text that's stored in manager.txt. Now, as I said a minute ago, the most common use of sed is to act as a command line version of find and replace. Let's say you want to replace the text of assistant with the text of assistant to be. To do that, you would use the substitute command instead. The substitute command is represented by the character S. So let me show you how that works. We'll start out with our sed command. Next, we'll put our sed script in single quotes. We'll tell sed to perform a substitution by specifying the letter S. After the S, we use a forward slash followed by the text we want to substitute, and then another forward slash. In this case, that text is assistant. By the way, the forward slash is acting as a delimiter, and the text between the forward slashes is called the search pattern. This search pattern is actually a regular expression, so you can make very advanced searches if you want to. In this case, we're keeping things simple to demonstrate the concept of finding and replacing some text using sed. Next, we'll type the text that is going to replace the previously specified text. We want to change assistant to assistant to be, so we'll type this. Next, we'll close our substitution with another forward they searched for. Instead, we completely replaced it with brand new text. It should probably go without saying that said is case sensitive by default. So here's an example of that. Notice that the lowercase text of my wife was not substituted. That's because it wasn't an exact match. If nothing matches, said doesn't perform any alterations and therefore the text is returned without alteration. If you want to perform a case-insensitive search, you'll need to supply a flag. So really, the format of the said S command is this. You have S / and then a search pattern, another / to terminate the search pattern, and the replacement string, another / and then any flags you want to use. So I'm just going to type Control-C here because I don't want to execute that command. I just want to quit that command line there without running it. So we're going to supply the I flag to the command, which you can think of as standing for insensitive. Now the text gets replaced because you told said to ignore case. By the way, and it strikes me as a little funny, you can also use a capital I as the flag to do this insensitive case matching. So this command works as well. Let's add some more lines to our love.txt file and see how said handles that. Notice that I've used two greater than signs, and that causes text to be appended to the file. If I just used one, it would have truncated the file. But I was careful here and used two, so we can look at our contents here. And sure enough, there are 2 lines in that file. So let's go ahead and add a third line. Okay, there it is, love.txt with 3 lines. Now let's try the replacement command again. What happens is that said reads one line from the file and executes the set commands in quotes against that line. Next, it moves on to the next line and does the same thing until it reaches the end of the file. You'll see that my wife was replaced by the word said on lines 1 and 3. Line 2 was unchanged because our search pattern of my wife was not found on that line. Let's add yet another line to this file to demonstrate another important concept. Now let's run the replacement command again. Notice that on the last line, only the first occurrence of my wife was replaced. It says, I love said, and my wife loves me. Also, my wife loves the cat. By default, said just replaces the first occurrence of the search pattern on a line. To override this behavior, we'll need to use the G flag. You can think of G as standing for global, as in a global replace. Now the last line says that I love said and said loves me. Also said loves the cat. If you want to replace the second occurrence of the search pattern, use the number 2 as a flag. If you want to replace the third occurrence, use 3, the fourth, use 4, etc., etc. So let's do this. This time, none of the first occurrences of the text of my wife were replaced, but only the second occurrences were. On the line where only one occurrence of my wife existed, that line was unaltered because there was no second occurrence. On the last line where my wife appears 3 times, only the second one was changed. By and the original file is left unaltered. So there you have it, the original file with the original text and the new file with the redirected and altered text. If you want Sed to alter the file, use the -I option to Sed, which you can think of as in-place editing. If you want Sed to make a backup copy of the file before it alters it, supply it with some text right after the -I, and Sed will append that text to the copy of the file. So now we have our original file named love.txt and another one named love.txt.bak. Sed has performed an in-place edit of the original file, so let's look at that now. So there you can see where Sed has replaced the text of my wife where appropriate given the command we ran. If we look at the backup file, we'll see that it has the original text in it. It's important that you don't use a space after the -I option. If you do, you'll get an error. So let me demonstrate that here. So this is what not to do. Okay, notice I'm using a space. This is going to cause an error. So sure enough, we get an error. That is one little gotcha you can avoid. So just do not use a space after -I. If you only want to save the lines where matches were made, you can use the W flag followed by a file name. So let's do this. Let's change love to like. We'll do a global replace so that no matter how many times love appears on the line, it will get replaced by like. And then we'll use the W flag and a file name after it. So we'll use like.txt. And then the file we're going to use as input is love.txt. In this example, Sed displays the entire contents of the love.txt file to the screen with any replacements it made, and it created a new file named like.txt that only contains the lines where the replacements were performed. So let's look at that like.txt file now. While we're talking about input and output, I would like to point out that Sed can be used in a pipeline instead of specifying a file to work on. The simplest example would be to cat a file and type that to Sed like this. That is the exact same thing as doing this. This is a very common pattern with Linux commands where they can be given a file to operate on, or they can use the data sent through a pipe to operate on. We've seen this with other commands such as cut, awk, sort, unique, and others. Command pipelining is very powerful because you string as many commands together as needed to make the data look the way you want it to. I'm going to generate some text to work on with an echo command. Let's say we want to change /home/Jason to be /export/users/JasonC. The challenging thing about this is that the strings we want to manipulate have forward slashes in them, and we've been using forward slashes as a delimiter with Sed. One way to get around this is to escape the forward slashes. I'm going to show you a better way in just a second, but let's see how we would do it with escaping first. Now, to escape a character, simply precede it with a backslash. So we're starting our search pattern with a forward slash, but the next forward slash isn't a delimiter, so it needs to be escaped. So we're going to use a backslash to escape this forward slash. Same thing again here. So now we end our search pattern with a forward slash, and again our next pattern starts with a forward slash, so we have to escape it here. Again, we're escaping the forward slash, and yet again, and then finally we're closing out our command here. That feels like a lot to keep straight, and it's easy to make a typing mistake in this situation. A nice feature with Sed is that you can use any character as the delimiter. So let's use a pound sign instead. So the first character that follows the S will be treated as the delimiter no matter what that character is. So let me give you an example here. I'm going to use a pound sign, and now Sed any character works as a delimiter, let's use another character. How about a colon this time? Okay, that works as well. So you get the idea. If you need to use forward slashes in your search pattern or replacement text, choose a different delimiter other than the forward slash. Alright, so enough with actually performing substitutions. Let's take a second here to talk about when you would actually want to perform them. One idea is to use templates or template files. For example, if you are constantly deploying new websites and use the same configuration except for the website name, then it would be a good idea to create a template file that contains all the standard configuration and a placeholder for the website name. Then you could use sed to simply replace all the placeholders with the actual website name when you're ready to deploy it. Another example of when you could use sed's substitution feature is when you are migrating from one server to another, or when you are using a restore of one server to create another new server. In this example, you would need to find and replace the old host name with a new one for all the files in the etc directory. Files such as etchost and maybe ethostname, and there could be others depending on that system's configuration. Yet another example would be when you are copying configuration for a given service from one host to another. You might find yourself doing this, especially if you are working on clusters. You would just copy the configuration from one host to the new host that you are adding to the cluster. Typically, you'll need to change the host name in the configuration file, and you could use sed to do this for you. Sed would be especially helpful if that host name appeared many times in that configuration. Okay, so that's pretty much it with the sed substitution command. Let's say we want to remove or delete some lines with sed. Well, how you do that is with the d command. Let's review the contents of our love.txt file. Let's say we want to remove the line that says this is line 2. All you have to do is come up with a search pattern that will match that line and not the other ones. So we could use a search pattern of this because the word this only appears on the line we want to delete. Our search pattern is this and the command is d. So to be clear here, the syntax is a delimiter, and by default we use the forward slash as the delimiter, followed by the search pattern and a closing delimiter. Again, this is a forward slash, and finally a d, which tells sed to delete the line that matches the provided pattern. We can see that this worked as our desired line is gone. Let's say we want to remove all the lines that contain the search pattern of love. Here's how we would do that. So now all the lines that match love are gone. Sometimes when I'm working with a configuration file with many lines, I like to strip out the comments and blank lines to compact the output. That way I can see just the configuration and nothing else. It makes it easier to read, at least it does for me. I'm going to create an example configuration file to demonstrate this concept with. So this sample made-up configuration file is just a few lines long, but you can easily imagine one with many more lines. First, let's remove the comments. Remember that the search pattern is actually a regular expression. In regular expressions, the caret symbol matches the beginning of a line. It matches a position and not a character. So if we want to match all the lines that start with a pound sign, we use caret pound sign. This makes deleted lines that started with a pound sign, it deleted blank lines, it also changed Apache to HTTPD. Just to be thorough, I want to share with you another way to execute multiple sed commands. Maybe I want to show you this just in case you happen to see it in a script or in someone else's work. That way you'll know exactly what is going on. So the other way to do this is to use multiple -E options to sed, one for each sed command to execute. Sed also allows you to specify a file containing the sed command. So let's demonstrate this now. I'm going to create a file using the echo command here. Of course, you can use an editor if you want to. So what we've done here is put one sed command per line. Now we use the -F option and supply the path to the file that has the sed commands in it. So we can do this, sed -F, and then the path to our file, and then the path to the file that we want to use as input. So here again we get the exact same result. Before we wrap up this lesson on sed, let's take a look at using addresses. An address determines on what lines the sed command will be executed on. If no address is given, the command is performed on all lines. An address is specified before the sed command. The simplest of addresses is a line number. Here are the contents of our sample configuration file to refresh our memories. Here's an example that will only execute against line 2 of the file. As you can see, the search pattern of Apache was replaced by HTTPD only on the second line. There's also a match on the last line of the file, but that was left alone because it didn't match the address of line 2. By the way, some people do not use spaces after the address, so this is the same command without that extra space. You can also use a regular expression as an address to match lines. Let's say you want to replace Apache with HTTPD, but only on lines that contain the word group. As you can see, Apache was changed to HTTPD only on the line that also contained the word group. You can also specify a range by separating two address specifications with a comma. For example, if we wanted to change the word run to execute, but only on lines 1 through 3, we would do this. There is only one occurrence of run from lines 1 through 3, and it was changed. The occurrence on line 4 was not. So let's extend the range to include line 4. Again, you can use regular expressions instead of line numbers. Let's say we want to change run to execute, starting with a line that matches #user and ending at the next blank line. So here's how we would do that. So there you can see that every instance of run that was in between the line that started with #user and the next blank line was exchanged with a text execute. Of course, there was only one match, so only one substitution was made, but you get the point. You could specify a large portion of the file if you wanted to, one starting point with another starting point as your address, and then change everything in that section while leaving everything else alone. It's very powerful to use addresses with sed. In this lesson, you learned the most common use case of sed, which is to perform text substitutions. You learned how to replace specific occurrences as well as how to replace all occurrences of the search pattern. In addition to
From there, you learned how to save the alterations performed by SED, as well as how to make backups of the original file so that your data is safe. Next, you learned 3 different ways to execute multiple SED commands on the same set of data. Finally, you learned how to use addresses to work on very specific sections of input.
I wanted to share with you a couple of scripts that I use during the creation of courses like this one. Shell scripts don't have to be long and complex. They can be made up of something that is just hard to remember or hard to type at the command line, something that would be lengthy at the command line, or just something that you happen to do often. Every time I record one of these videos, I have to do some audio processing, so I wrote a shell script to take care of that for me. When I record a video, it gets saved in MP4 format. Due to the mic I'm using, the audio is just saved on one channel. I use this script to extract the audio and then convert it to a mono file so that the sound will come out of both speakers. See, I start the script with a shebang, a brief description of what it does, and then I start defining my variables. The input file is $1, which is what we pass in on the command line. I use the dir name command to extract the directory portion of the input file, and this way I can use that directory later on in the script. The base name command does the opposite of the dir name command, which is it returns the name of just the file without a path. The -s option in this case just removes the .mp4 suffix. I create a temp file with a suffix of .wav that I'm going to use to extract the audio with, and then the out file will consist of the directory name followed by the base name of the file that was passed in, but now it's going to have the .wav extension instead of the .mp4 extension. So the abconvert command just extracts the audio from the input file and saves it as a WAV file. Next, the sox command will take the audio from channel 1 and then save it to a mono file so that the audio comes out both speakers. Next, I display the name of the file to the screen so I can easily copy and paste it if I want to. And finally, I clean up my temp file by removing it. This next script takes my slides that are in PDF format and creates a series of PNG files that I can use with my video editing software. Again, the first line is a shebang, and then a description of what the program does and even how to use it. And the first thing we do is pass in a PDF file, and we assign that to the PDF variable. Next, I create a slides variable, and I replace the .pdf with -slides.png in the file name. From there, I substitute hyphens for spaces, and then I convert everything to lowercase. Sometimes my PDF files are saved in camel case or uppercase or whatever, and I just want these images to be all in lowercase. If a path was provided, I just use the base name command to strip that path off because I want to save these images in the directory that I launched the script in. Finally, I use the convert command to do the actual conversion from the PDF file to a series of PNG images. I wanted to mention that the first 3 slides commands there are some bashisms that you can use to do some substitution like I did, or changing the case and that sort of thing. So if you're not using the bash shell, I could have used something like the sed tool to do these replacements with, or tr to translate from uppercase to lowercase, for example. I find myself writing shell scripts all the time, especially if I'm going to be doing something more than just a couple of times, or if I have to remember the options for a command that I don't use often. For example, I don't use avconvert during my normal daily activities, so it's hard for me to remember those options since I use them rarely. Hopefully you've enjoyed this video, and it'll give you some ideas of how you can automate the work that you do.